Hello all. Today we're looking at solving quadratic inequalities. So we have been, everything so far has been quadratic expressions or quadratic equations, but now we're looking at inequalities, so taking it to that next level. If we look at this example here, we have x squared minus 5x minus 14. When is that greater than 0? Well, we could factorize that and we get this factorization through inspection. And we run into a dead end because we can only apply the null factor law to an equation. It doesn't hold for an inequality. We could continue if we change the inequality to an equal sign like what is done right here. And that allows us to find out what the intercepts are if we graphed this expression. But it's not helping us any further than that. So to solve inequalities, okay, and actually I should change this to say inequalities, we need to sketch them. And I'll explain why we need to sketch them or how sketching can help us. We need to go back and remember that an expression or equations are a process of having an input, doing something to that input and getting an output. That's what a function does. Takes something, does a couple things to it, or one thing, or lots of things, and spits out something else at the end. So let's think of this as we start with x. We have, let's say, an expression or an equation. And we get some output, okay, which we call y. We have input, we do something to it, and we get our output. When we think in these terms, okay, we're used to, that's what the equation symbol here is. If we have x squared minus 5x minus 14, okay, that equation symbol is just saying let. Okay, let everything on the left-hand side, whatever we do to it all, we'll just now store it as y. Think about storing numbers. And we can think of like a variable table, 1, 2, 3. Okay, whatever we put in on the left-hand side, whatever we get, we let it equal to y. So if we think of that in terms of a let and an input and output, we can realize we can work, let me just erase this quickly, is we can think of inequality in terms of input and output. What this is saying, instead of all this complex bit on the left, that is also equivalent to when is y greater than 0. Because we could think of this initial expression as our function doing something to our original input x, and we don't need to leave it written like that. We could call that whole expression anything. We could let it equal to y, we could let it equal to a, we could let it equal to m, whatever we want. And then once we think in those terms, we can realize that we're just asking is when is that final output, in this case m or a or y, whatever we want to call it, when is that final output greater than 0? So whenever you see an inequality like this, think of, okay, I've got my original input a, do something to it, I get an output, I can call that output whatever I want. I suggest, of course, y, call it y. And then you can think of it much more simply in terms of, I want to know whenever y is greater than 0. Now, how do we know when y is greater than 0? Well, let's sketch a function. Sketch our function, then we can read off. When is it great? When is the y value greater than 0? So, I have gone ahead and sketched this for you. I could pretty much say let x squared minus 5x minus 14 equal to y. And now I've sketched that equation, and I want to know when y is greater than 0, and I can read that. So of y and x, so when is y greater than 0? Well, y is greater than 0 when any of the values are in here. So when does that occur? Well, these all have values that are y greater than 0. These all have values y greater than 0. So that part of the graph has values y greater than 0. When do those occur? Well, those occur when we put in an x value all along here. Any of those x values result in one of these y values that is greater than 0. And same over here. We could pick any of these x values, put it back in our function. We can see graphically it results in y being greater than 0. So to solve, we need to state the region of the curve that is greater than 0. Okay, as we can see, it's above x-axis is talking about this bit here. We need results of y greater than 0 or above the x-axis. So when does that occur? That was at 7 and this is at -2. So it occurs when x is less than -2 and also when x is greater than 7. It's not including -2. We aren't putting the including symbols because at -2 and 7, y is equal to 0. That point there and that point there, which means it's not greater than 0. It's only equal to. Doesn't meet the requirements. What are we in? 6 minutes. Okay, so let's get going and do an example. So solve the equation x squared minus 7x plus 12. Again, equation inequality. So I'm going to let x squared minus 7x plus 12 equal to y. Therefore, I'm trying to find when y is less than or equal to 0. Let's think about that. So I can factorize all of this. I'm left with x bracket y. So multiply to give me 12, add to give me -7. That's going to be -3 and x minus 4. -3 times -4 is positive 12. -3 take away 4 is -7. Okay. I'm going to let y equal to 0. So I now get x minus 3 bracket x minus 4 equals 0 because I'm trying to find my intercepts to graph this. So I get x equals 3 and x equals 4. Now I have intercepts to graph. As I said before, you would normally use a ruler to do this. Okay, I'm going to call, there's x equals 3, there's x equals 4. Go through. Now it's a positive quadratic because the x squared term is positive. That means it's our regular U shape. So the graph will be something like that. Now, do we need to sketch the turning point? Do we need to find out what the y-intercept is? For this question, we aren't being asked to sketch a graph. Okay, so all those non-negotiables from our previous lesson about having to label in coordinate form, having intercept, turning points, consistent scale, all that doesn't actually apply here. Those non-negotiables only apply when your final output is a sketch. This, we're just using a sketch tile to solve another problem, so you only need to do as much as you require, which in this case is 2 intercepts and a rough line. And then we look at that rough line. So I want to know when y is less than or equal to 0. So when is y less than or equal to 0? Well, that would be any y values here. That's when y is less than or equal to 0, which means it's this part of the line. Okay. And this time we can include 0, so it's going to include our intercepts as well. All that part of the line y is less than or equal to 0. When is that occurring? Well, that's occurring between, that was x equals 3 and this is x equals 4. So, to solve this equation, that occurs when x is greater than 3, but also less than 4. You could have written this as, first looking at this, okay, I need to be, x is greater than 3, and then also looking at the right-hand side of it, you could see that, well, x needs to be less than 4. You can combine those and write it like that. But that's how we go about it. So pretty straightforward, hopefully. Hopefully this makes sense. If you need help, ask in the Google Classroom or stick a comment in this video. That's completely fine. I will get notifications of that. What else? The only other things to point out is sometimes the factorization is not as easy as just inspection. Sometimes you might have to do the cross method. Sometimes you might have to use completing the square. There's an opportunity for you to have a go here. The only thing different with this one is it is a negative quadratic, so it's going to be an n-based shape. So make sure you're aware of that. And we want to know when we let negative x squared minus 3x plus 4 equal to y. We want to know in this case when is y less than 0. That's it. Have a go yourself, and yeah, like I said, ask questions in Google Classroom. See you and have a good day.